All right. Why don't we get started? Maybe I'll post this up on Piazza. I thought it was kind of fun. Not everybody in the world is a true believer in ER diagrams, including my mom. So take your lessons as you get them. But you will do more exciting things than building accounts receivable applications, I promise. Okay. We are ready to start on a new topic, which is great because I've kind of had it with functional dependencies. I don't know about you guys, but I think 3 lectures was plenty. So if you remember our block diagram of the database, we kind of started from the bottom with the disk layouts and the buffer management, the access methods, query processing algorithms, and then we kind of came from the top with SQL. And it all meets in the middle today with the query optimizer. Okay, so we're going to connect declarative queries that say what they want but not how to get it, with imperative code, all that stuff we learned how to implement. We connect that with the query optimizer. This is where the magic happens, if you will. It's pretty straightforward magic once you get to know it. It's also old magic, but it's good magic. Okay, so let's get started. A little review. What is the space of things we need to worry about when we think about optimizing a query? Well, if it's a query on a single table, we know that there's a choice of operations. We could choose to scan tables that are in heap file format, or we could use indexes. And this might depend on how many buffer pool pages we have. It might depend on some statistics about the data. We'll see all these sorts of things today. What about if we're thinking about joins? Well, there's lots of different join algorithms to choose from. So, for example, we know that this chunk, or block, as they call it in the book, nested loops join, is nice and simple to implement, and it takes good advantage of that extra memory by bringing things in chunks. Index nested loops joins, though, could be even better if, like you have a very small outer relation and a very big indexed inner relation, because then you just do a few index lookups, one per tuple in the outer relation, and life is good. So if you have a really big table, put an index on it, then little tables will join with it nicely with an index nested loops join. So that's good. We know that sort merge join does well with modest amounts of memory because it only needs square root the size of the bigger table, right? So that's good. It's bad with duplicates. What do I mean by that? Oh, well, when you're actually doing the join part, right, the duplicates create that cross-product effect. But you would have to do that in any algorithm, actually, because you have to form those pairs. So I'm not really sure I even like that characterization. I think that's wrong. I probably put it there late one night, and I should take it back out. So I'm just going to do that. It's just fine. Okay, so sort merge join is nice. It's predictable. It's got a small memory footprint and a lion. There we go. Hash join is also very much like sort merge join. It's fast. It has some issues with skewed data. Remember that hash join is particularly nice if one of the relations is smaller, because you only have to have square root of the smaller relation for hash join. Whereas with sort merge join, you may recall we needed the square root of the bigger relation as well to sort it. Now, this is great, and this is enough to get you into trouble building a query optimizer. And if you look at the query optimizer in something like MySQL, it'll kind of have stuff like this in it. A bunch of kind of rule. Actually, I haven't looked at it in a long time. Maybe it's better by now. But the way it used to be anyway, a bunch of kind of rules of thumb. It would always look for indexes. When it could find them, it would choose an index nested loops join. If it couldn't find any relevant indexes, then it would choose a sort merge join, I think. And if it wasn't an equality query, it would choose a nested loops join. So that's okay, but we could be more principled about this. We could put some thought into this, and we could get this, in some sense, right. All right, so that's what we're going to work towards today, is not having this be a pile of heuristics, but something a little more principled. All right, so a little overview of kind of the big picture. You take your query, and you can convert it directly into relational algebra in a naive way, right? In some sense, even though this relational algebra expression down here seems to have some decisions baked into it, like the selection is outside of the parentheses, the join has reserves on the left and sailors on the right, it's a little more prescriptive maybe than the SQL, which is fully declarative. The truth is, and of course this corresponds exactly to this plan tree. We could be messing with trees, or we could be messing with the mapping from queries to trees, and that's equivalent. All right, so keep in mind as we talk today that we will, in the spirit of what's in the book, talk about how we go from a declarative query to one of many trees. All right, where a tree looks like that. Plan trees. But you could equivalently say, we'll go from the query, we'll generate one plan tree, and then we'll just start to massage it in every way we can to change it into other equivalent plan trees. And that's going to be the same idea. It's just a different way of getting at it. Our approach is going to be, from this query, we could generate one of many of these plan trees, and we'll generate lots of them. Okay. Anyway, the basic idea is we convert from query to relational algebra, which can be drawn as a tree, right? And for each operator in that tree, this is still logical, right? This is still just a description of the algebra. It doesn't say how physically to implement it. So each operator, like a join or a selection or a table access, those could be converted into one of many algorithms, right? So that's called a physical plan. So we'll go from a query to a logical plan to a physical plan. And of course, we can reorder the logical plan as well. So there's a lot of decisions to make. Let's be a little more specific. What is a plan? A plan is going to be a tree of relational operators, so it's a relational algebra expression, where every operator has an algorithm associated with it. So we know how we're implementing each one of these steps in the plan. So that's going to be a query plan. And of course, each one of those relational algebra operators is in essence being mapped to an iterator implementation. Right? So that's all we're doing. We're taking that relational algebra expression and we're mapping it into a tree of iterators, where each iterator is an actual implementation, like you guys did in Spark, right, of an algorithm. Okay, so you get a tree of iterators instead of a tree of relational algebra operators. And there's three main issues we have to think about when we're doing this. The first question is, what plans are legal? So if you give me a query, what are all the possible ways of evaluating that query? So we need to characterize in some sense what the search space is of all possible ways of executing this query. That's issue number one. Issue number two, suppose I told you there are 20 million possible query plans here. Pick the best one. Well, then you'd have to have some notion of what's best, right? You can go through all 20 million of them, find the best one. What's best? Well, we need to be able to estimate the cost of a plan, preferably without executing the plan, because that would mean running the query 20 million times to choose how to run it once. Which would be a pretty bad strategy, right? So we want a way to estimate the cost of plans without actually running them. And then the third thing is, okay, there's 20 million plans, but do we really have to look at all of them, or is there a way to prune our search? Can we do a better job searching in that space of 20 million plans? So those are the three pieces. What's the search space? How do you estimate costs in that search space? And given that you know the space and the cost metric, how can you search in the search space efficiently? So that's kind of the game of query optimization. And one of the nice things about it is that we can take each one of those questions kind of independently and then put them back together, which is nice. So the problem breaks down and componentizes quite well. Ideally, we really want to find the best plan. It is, after all, called a query optimizer. It's supposed to find the optimum. That is pretty much infeasible in practice, and we'll talk about why. So what we're going to try to do is find a good plan and avoid really lousy plans. All right, and the reason for this is roughly has to do with probability and statistics. We're going to find a plan that's expected to be good in some statistical sense. Okay? But maybe we'll get unlucky one day. So be it. All right, but we're going to go for plans that are expected to be good and avoid plans that are going to be lousy. All right, so that's the goal. Okay, so this is kind of what it looks like from a block diagram perspective under the covers of a query optimizer. A query comes in, it gets parsed into an abstract syntax tree of some kind. Hopefully you took a compiler's class or you've played with a parser. But nothing interesting happens other than we turn a string into an expression we can manipulate. And then that thing goes into the query optimizer. And what the query optimizer does is it engages in something of a dependency loop between something that generates multiple plans and something that estimates the cost of those plans. All right, so those are two separable components in the query optimizer that call each other back and forth. Okay? And the plan cost estimator in particular is going to have to look in the catalog to look at the schemas of the relations and make sense of them, and also to look at statistics about the relations. And we'll talk about what those statistics will be, because they're going to determine the costs of our query operators. And I'll remind you of some of this, and then we'll look at some new things today that we haven't thought about before as well. Usually, actually, before you get into this whole thing, so this is the traditional query optimizer, but actually there's usually an additional step after the query parser, which takes queries and syntactically rewrites them in ways that are guaranteed to make life easier for the optimizer. And the most standard rewrite is to turn a subquery into a join. So you wrote something that says where exists, and then you had a subquery. And we talked about if you do that implicitly, you get kind of a nested loops effect, right? Because the outer query is for each tuple of the outer query, where exists, and then you run a subquery, right? So if you can convince the query optimizer this is just a join, then the query optimizer can apply its usual join optimization problems and doesn't have to think about multiple nested queries. So we'll try to flatten all our queries in this rewriting step so that the query optimizer is going to deal with just select from, where, group by having, with no nested queries. So we're not going to talk much about nested queries today on the theory that if we possibly can, we're going to unnest then flatten them. All right, I won't actually talk about query flattening at all in this class because it's very fussy. It was also my first job after college, and I don't like to look back at it. So there. And I wrote it down, too, so you can read about it. All right. So let's go through some examples of query optimization to get a flavor. We did a bit of this in the past. We're going to do it a little more in detail today to kind of get you really thinking like a query optimizer, which takes some practice. Okay. So here's our schema, sailors and reserves, once again. It's boring to keep using the same schema, but it also allows us to maybe remember what we're talking about. And so the key statistics here, I won't read them all through, but remember, and we'll come back to this, there's 1,000 pages of reserves, and there's 100 boats, okay? So there's 100,000 reservations, 100 tuples per page, 1,000 pages for 100 boats. All right, each tuple's 50 bytes long, blah, blah, blah. There's 500 pages of sailors over 10 different ratings. So there's 20,000 sailors at 10 different ratings, right? And we have 5 pages in our buffer pool, which we'll need to cost out our algorithms. So let's look at a motivating example. This is an initial query plan. This is going to be our first cut. All right, we're going to take sailors join reserves using a page-oriented nested loop string, chunk nested loop string, but just one page of the outer, and then you scan the inner. So the chunk size is 1 page. All right, and what are we going to do here? We're going to read in sailors. So that's a cost of 500 IOs, right? Because if you remember correctly, the sailors relation had 500 pages in it. And for each page of sailors, we're going to scan reserves, because page-oriented nested loop string. So it's 500 times 1,000. That's the cost. Now, this is not the worst plan you could come up with. It's just a bad one, all right? It's not the worst, all right? But there's a lot of things we could do that's better. Maybe we could do the selections before we do the join so that fewer tuples are fed into that join algorithm, and the join could do less work. We didn't take advantage of any indexes, right? So there's a bunch of things we could do to make this better. So let's look at some of them. Let's evaluate how we could make this better. Here's an alternative plan where the selections are going to get pushed down. We're still not going to use indexes, but what we're going to do is we're going to take these selections. This is the same thing you saw on the previous slide. We're going to push those selections below the join. Okay? And in this case, rating greater than 5, rating is from the sailors table. So we're going to apply it to the sailors table, and when it says on the fly, what that means is as we scan the sailors table, when we see a tuple, for each tuple, we'll look at this rating, and we'll decide if it's greater than 5 or not. If it's less than 5, we'll throw the tuple away. Right, so we pay no I/O cost for that selection because it just happens as we're scanning the sailors table. That's what I mean by on the fly. So from an I/O perspective, the selection is free. But now the join is going to do a lot less joining. All right? How much less joining? Well, rating greater than 5. What would be a good way to estimate how much stuff that throws away? Oh, that's a really fancy way to do it, yes. So one way you could do it is you could take a sample of these sailors and you could try to figure out the distribution of sailors and estimate what percentage of them are greater than 5. But suppose I tell you that we don't have time for that and we want to do something just kind of wet finger. Yeah. Great. Let's assume ratings are evenly distributed. Ratings go from 1 to 10. Like half-ish of the sailors have rating greater than 5, which seems wrong, right? Because it's harder to get a high rating, but let's ignore that for the time being, okay? So we'll assume that half the sailors get through this selection. Wet finger technique, all right? And is that good enough? Sometimes. All right, for now, let's do it, because I don't want to spend a lot of time talking about estimation just yet of these predicates. So if we do that, then we're going to take half as many passes on reserves. So it's going to be 500 plus 250 times 1,000, right? So it's going to be 250,000, 500 IOs. We saved a factor of 2 because we did a factor of 2 fewer passes of reserves, right? Now, maybe it wasn't a factor of 2. Maybe it was a factor of 1.8 or something. Let's not worry about it too much. Okay, so that's that plan. Maybe we should push the other selection down. It's a selection on boats. We could push it down below the join to filter out tuples of reserves, right? So let's do that. And we'll do it on the fly as well. So as we scan in a page of sailors, And as we're scanning the reserves table, we're going to throw out any boats unless they equal 100. Right, as we take that pass of the boats table. So grab a page of sailors, scan reserves. We're throwing out reserves tuples as we go. How much IO do we save? Well, you're probably thinking boat ID equals 100, there's 100 boats, something, 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 right? All right, but you got to think about the algorithm too. So what changes in the algorithm by filtering early on the on the inner loop of a nested loops join? For each page of the outer relation, we scan the inner relation, throwing away tuples as we go. And then we get another page of the outer, we scan the inner relation again, throwing away tuples as we go. Right? It doesn't change any IOs, actually, to filter that boat ID equals 100 the way we're describing it, because we're still going to scan reserves all the way through for every page of sailors. Yes, we're going to throw the reserves away, and that will, the reserves away, and that will save us some in-memory computation maybe to do the joins. But it won't save us any IO because we're going to take a full pass of reserves for every page of sailors. So that didn't save us anything. All right, so sometimes this is a little counterintuitive. Does that make sense to everybody? It just has to do with, keep track of what these algorithms are up to with their IOs. Okay, so let's stick with the one we had before. What did we change? Oh, we flipped the order around, right? Now, we got reserves as the outer loop and sailors as the inner loop. Okay, let's see. We got to remember how big these two things were. Reserves. Where are we? We are currently on. Gotta stay organized. We're on slide 11. All right. Reserves is 1,000 pages. Sailors is 500 pages. Okay. So now we're going to say 1,000 plus 1,000 times 500, right? Does that sound right? Oh no, because we're filtering on boat ID equals 100. Which is 1/100th of the boats if we make the same uniform distribution assumption we made before. So 1/100th of 1,000 pages is how many pages? 10. So it's 10 passes of the sailors table, which is 5,000 pages big, right? So it's 1,000 plus 10 times 5,000 equals 6,000. That's awesome, all right? That was a big savings. So pushing down the selection on the right-hand side made no difference, but switching the join around and then pushing this nice highly selective predicate, only boat ID equals 100 down the left-hand side. That was a big win. Okay, let's keep going with this for a little bit longer. This is our current winning plan. Now let's do something we didn't do last time. We could have done it before, but we didn't. We're going to push the selection down, but we're also going to cache the result, which probably we should have done in the first place. So we'll scan reserves. The first time we take a pass of sailors, we're going to take out those guys with ratings greater than 5 and write it to a temporary file called T2. And from then on, we're just going to scan T2 every time we read a page of reserves. Right? So there's sort of a different plan here, really, that's going on. You might even say there's a different physical operator for selection. It's a materialization operator. It materializes its output. Okay? If we do that, well, you got to work this out. Reserves is 1,000. The first time you read sailors, it's 500, and it costs $250 to write it down. That's the temp cost for writing. And then for every page of reserves, we scan the temp table, which is 250 big. Right? So we actually, this is getting better. Still better. Okay, now let's flip the order of the joins around again. But let's play the trick we should have played in the first place, which is to write that reserves relation to a temp. Now what do we got? All right, this is going to get better. We've got 500 to scan sailors, 1,000 to read reserves, but only 1/100th of it gets written back because there's 100 different boat IDs, and we're only picking one of them. All right, so it's 10 to write it back. Sorry, 500 to scan sailors, 1,000 to scan reserves, 10 to write the temp, and then 250 because of the selection on rating, times 10 to do the actual joining. Make sense? All right. So things are getting a little bit smaller. That one's probably in the noise. The difference between 4250 and 4010 could easily be swamped by our ridiculous estimates about uniformity, right? That boat IDs are uniformly distributed and ratings are uniformly distributed. But let's just go with our assumptions for now. What about sort, merge, join? We haven't thought about that. Let's go through the exercise. So remember, we're going to sort, merge, join the results of the selections. So sort, merge, joining BID, we're only going to sort, merge, join, 10 pages, right? And sort, merge, joining, rating, we're going to sort, merge, join 250 pages. So this is not that bad. So scan reserves and write the temp. That's 10 pages, 10. Scan sailors and write the temp, which is 250 pages. That's a total of 750. Sorting T1 is 2 pass on those 10 pages. Sorting T2, I think, is an extra pass, hence the 2 times 4 times 250, because we've only got 5 pages of buffer pool, right? So we're going to sort in 2 passes for T1 and 3 passes for T2. And then merge, which is just read the outputs. That's a total of 2,300. Add that all up, it's 4060. It's actually a little bit cheaper than what we had before, right? Before we had 4010. No, it's a little bit more expensive, so it didn't pay off yet. All right. Oh, yeah. Now, what if we weren't using page-oriented nested loops? We were using chunk-oriented nested loops. We could bring in more pages of the outer for every scan of the inner. We could get the total cost down to $27.70. So nested loops join is actually looking pretty good. Oh, here's another trick we haven't played yet. We could push those projections down as well. So what columns do we need to generate S-name at the output? Well, we don't need all the columns from reserves and sailors. For reserves and sailors, we need enough of the columns to do the selections and the join and the projection and nothing else, right? We just need the columns that are referenced upstream or sort of downstream, up on the board. So if you start pushing the projections, T1 only needs SID. T2 only needs SID and name after the selections, okay? And so T1 will actually, once you sort of pare away the columns, fit in 3 pages. And the cost of the chunk nested loops join is really cheap then. So you're only paying for the cost of reading and materializing, and the total ends up less than 2,000. All right, so we went through a lot of examples. Let's do one more, which is what about indexes? So we got the cost down under 2,000. I will just remind you before we move on. The initial cost was $500,500. Okay, so this makes a big difference. All right, what about with indexes? Well, got to think about whether they're clustered or not, right? Because this is going to affect the number of IOs we do. If we have a clustered index on the boat ID of reserves, in the example on the right, so reserves is the outer relation, we will access to get all of the boats with ID 100, of which there are a lot. I don't forget the numbers. There are a bunch of them. So you want it to be clustered because you're going to scan a whole bunch of things that have BID equals 100. But if they're all, it's 1,000 tuples. There we go. If they're all together, then it's 1,000 tuples, 100 tuples per page. It's only 10 pages worth of heap file that we'll go look at to get the reserves tuples. Okay, so that index lookup, select BID equals 100 on reserves, is going to result in 10 pages of heap file scan, plus maybe the cost to go down the index, but let's say that's free. And then we can do an index nested loops join on the fly. We don't have to write down the result of that index lookup. Tuples come out of the index, they stream right into this nested loops join, right? And we scan sailors for each one of these. Now, pushing down projections into an index nested loops join doesn't really help because we're not storing the output of anything, right? Everything's streaming past, and so there's no IOs to write anything, so there's no benefit to throwing away columns. At least not on disk, okay? Because it's all just streaming past. Ooh, so what about an index on the right-hand side, on sailors? The join column is SID, okay? And SID in sailors is a key. Agreed? Sailor ID. If it's a key, that means there's only one tuple for every SID that's in the heap file. SID4 is in one place, SID6 is in another place. But there's only one SID4. So we don't actually need that heap file that index to even be clustered because we're never looking up ranges and we're never looking up duplicates. We're just doing point lookups of individuals in it. And so we can have an unclustered index on SID. That's totally fine. All right? Because we're using the index, it's not really all that meaningful to have the selection below the join. So think about this. You get a tuple from reserves. You're going to do an index lookup in the index on sailors by SID. And when you get the match, you send it to the output. Right? Does it matter whether you think about applying the selection after the join or before the join? It kind of doesn't matter from an I/O perspective. You got a tuple of reserves. You did a lookup into sailors. You could throw it away before you put them together in memory, or you could put them together in memory and throw it away after, but it wouldn't affect your I/O. Okay, so pushing down the selection on the right makes no real difference. All right. If you use this plan where you have the clustered index on the left, the unclustered index is fine on the right, you get down to 1210 IOs. All right, that was maybe a little tedious, yeah? All right, but hopefully give you a sense of why we hammered home the query execution algorithm cost so much in the first half of the class and on the midterm, because we want you to understand why this works. Now that you understand why we need to go through this plan space and exactly how you cost things out, you'll get a sense that you want to mechanize this. You don't want to figure this out on your own. Every time you write down a query or you think of, gee, there's something I want to do with my data, you don't want to do what I just did for the last 5 minutes. It's boring, right? You want an algorithm to do that for you. So that's what the query optimizer is going to be. All right? So to sum up, there are lots of different plans, even for a relatively simple query. There's exponentially many plans, folks. Right? There's a lot of plans. It's a hard, in the theoretical sense, problem to do query optimization. It's NP hard. People often think that they're better than the optimizer, and sometimes they are, and then they feel validated. But usually they're not better, and often they're worse, and usually it's way too boring to even worry about. So I don't understand why people are like, query optimizers get in my way. I want to write the code myself. Like, give me a break. At least look at what the query optimizer says, and if you think you could do better, you could tweak it, right? But like the idea that query optimizers are somehow in your way just is like crazy to me. All right? Because like who wants to enumerate an exponential space of shit? It's boring. All right, but MapReduce is like all about that. It's like, I want to write low-level code because it's great, because I'm a hacker. Maybe. And sometimes you do. Like if you're optimizing the same query, it's going to run every day. So I'll give you a really good example. Web search, all right? The basic lookup query at Google, when you type in a search key and it goes off and it goes to 100,000 machines and it gets you back the answer, that's one query plan pretty much. They have optimized the crap out of that query plan, I assure you. And somebody thought about it, and it's been refined by engineers over time. And as they add features to the ranking algorithm and stuff, the query plan changes. That's one where it's worth investing in doing it yourself. Like you don't want to give that one to the Oracle Query Optimizer and hope for the best. Okay? But most of the time, most settings, you're not going to want to do query optimization by hand. All right? Machines are very good at enumerating options. All right? It's all good. Now, having said all that, we will see very soon that these optimizers are making some pretty absurdly simple assumptions. We saw one already, which is oftentimes they make uniformity assumptions about the distribution of values. Oh, there's 10 ratings. That means 1/10 of the sailors have one rating and 1/10 have another. That's just not true, right? Super duper awesome sailor has fewer sailors in it than like beginning sailor. It's just that's the way the world is. So the statistics of it are places where we're going to maybe compromise, and it could lead these optimizers to do dumb things. Okay. So I gave you the good, I gave you the bad. What do we need to implement? We talked about this before, but let's write it down. Given that we have a closed set of operators, now this doesn't have to be relational databases and relational operators. This could be any declarative language you like. All right, so the same structure that we're going to learn about applies to XML query languages or JSON query languages or crazy Spark, MapReduce, make up your next query language. All right, this framework for query optimization applies. So we're going to set up this closed set of operators. What do I mean by closed? I mean that the output of one operator can be fed into the input of another. All right, so it's a closed language. You can construct sentences where any sentence in this language could be feed input to another operator in the language, like in algebra. So a closed set of operators, like, for example, relational operators take tables in and produce tables out, right? And then we're going to have encapsulation of these operators so that we know that they can be implemented we can string them together from an implementation perspective, a la iterators, so that we can keep composing them physically, not just logically, right? We can construct actual query plans. Given that, there's going to be some legal space of plans. And we're going to study the one for relational queries in this class, and it's pretty prototypical. You won't find a lot of things that are wildly different than relational queries. But there are some subtleties when you deal with JSON or XML or what have you. But for the most part, this is prototypical. We'll study relational queries and how the plan space works for those. So what are the equivalent queries? And somebody asked this like weeks and weeks ago when we studied the algebra. What are legal rewritings of the algebra? When can we push a selection below a join? Is that always correct, et cetera? So we have to figure that out, these relational equivalences. We also have to figure out the physical implementations. How many different join algorithms does our system have, and what are we going to choose between? Given that plan space, the cross product of all those options is going to create the space of all possible plans that are the same. Then we need to do cost estimation. Cost estimation is going to have two pieces. I give you an algorithm like sort, merge, join, and you write down the cost formula for sort, merge, join. That part we already studied. The second part, though, is size estimation. Usually the costs for these algorithms depend on the sizes of their inputs. So how do you estimate the size of the input to, say, a join when it's in the middle of a big tree full of joins? Because it depends on all the things below it. The size of the input to this guy depends on the sizes of the outputs of all the things streaming into it. So how do we estimate these sizes? And that'll be based, again, on some cost formulas and some, on that size estimation will be based on basic information about the base tables, which is in the catalogs, and then estimation procedures, which are statistical estimation procedures. In database optimization, it's called selectivity estimation. Okay? The book wants to call it reduction factors. It's the only place I've ever seen anyone use that phrase is in our textbook, but we'll use it in the slides so we're consistent. Most people call it selectivity. All right, so we'll have to figure out how to do this selectivity estimation. And then finally, given the plan space and a cost estimation, we'll need a search algorithm to sift through the plan space somewhat efficiently and find the lowest cost option. All right. What I will tell you is that the plan space is exponential for relational queries, and the problem is NP-hard. So the best search algorithm we'll find is still going to be exponential, but we can shave off some pretty significant factors from that by doing it intelligently. Okay, so we'll want a decent search algorithm. Okay, we're going to focus on the SystemR or Sellinger optimizer. So this is kind of the Bible of query optimization. It was written by this lady, Patricia Sellinger, who's still around. She's still at IBM leading projects. And everybody always references this paper. It's like the grandmommy of relational query optimization. So she's an awesome lady if you ever get to meet her. She's still around. Here are the highlights of the SystemR optimizer. SystemR, by the way, historical note, was IBM's research relational database. It was the first relational database that IBM got serious about. A lot of very influential computer science papers written on that project. They invented the transaction, which we're going to spend a lot of time learning about. They invented the query optimizer. They invented SQL. Okay, so this is a very influential project. Many of the leaders of the SystemR project were Berkeley alums, notably Jim Gray, the father of the transaction and the winner of the Turing Award, was Berkeley's first computer science PhD student. So SystemR is a very Berkeley project. But the competitor to SystemR was a Berkeley project here at Berkeley called Ingress. So you may have heard of something called Postgres. Postgres was post-Ingress. Ingress was the first research system built at Berkeley for relational databases, and that was also very influential. They invented things like views, and what else was in Ingress? They had a different query optimizer, which is somewhat forgotten, but actually pretty interesting nowadays. And they had some other important innovations in Ingress as well. They had a language called Quell. Both SystemR and Ingress led to companies. SystemR led originally to a company called Oracle because Larry Ellison read all the tech reports from IBM and just copied them and built a system. And the interesting thing was IBM, you have to imagine IBM at that time was kind of like Google is to the internet today. They just were like unstoppably huge. Every computer of note in the world was built by IBM. Most of the software that ran on those computers was built by IBM. It was just like this enormous thing. But they moved kind of slow. So Larry Ellison bet on Unix and mini computers, which at that time were considered kind of a toy. And he built Oracle with the idea that that market would be where he'd start and that market would grow. And he was completely 100% right. So the mainframe became less important, and Oracle's market became more important. Ingress tried to do the same thing, but just got their pants beat by Ellison. That guy's just a monster. So to hear the guys from Berkeley at the time talk about it, Ellison lied, cheated, and stole his way to success. But when I hear about it, I hear like, well, we got out-marketed and outsold. The Oracle guys were very aggressive, let's say. Anyway, SystemR very influential on both of those, both the IBM products and the Oracle products, and every relational database basically implements a SystemR optimizer. Okay, a little history. So it's an exponential algorithm, and it's an NP-hard problem, and so it only really works up to like a dozen joins, actually, which is a pretty small number, even for an exponential algorithm. 2 to the 12th doesn't sound that big, but there's a lot of constant factors going on. So usually you can only do this. Like if your from clause has 100 tables in it, you, first of all, are crazy. And you probably auto-generated your query from some other software. And second of all, your system will resort to heuristics if you give it a query like that. So this only works up to a decent size, like a dozen joins. All right, so this plan space is going to be really big. At minimum, let's prune it in this exponential space. A lot of plans share common subtrees. And if you have two plans and they have the same subtree, and that subtree was already a bad deal, then there's no reason to look at both of those plans. You should be able to figure out by looking at that subtree in one case that anything built out of this subtree is going to suck. Okay, and so let's not even consider plans that have this subtree. So we're going to do pruning of that sort using dynamic programming. All right, how many of you learned dynamic programming somewhere? Great, okay. This is a classic dynamic programming algorithm. And then we're going to have some heuristics as well, which we'll talk about, like left deep plans and Cartesian products being avoided. We'll talk about that in a minute. The cost estimation in the Selinger paper was really simple. It was about as simple as we were just describing. Uniformity assumptions and independence assumptions all over the place. Okay, but it actually worked pretty good in practice because the cost, think about the dynamic range of costs we saw for that simple query we looked at. It was like 500,000 IOs versus 2,000 IOs. Like you could be kind of wrong in there and still avoid doing 500,000 IOs. Right? You could get it down into the 4 figures. Right? So a little bit of wrongness isn't even so bad here because the dynamic range of the errors, the bad choices, are so bad relative to the respectable choices. Optimizing amongst the respectable choices for the best is almost not worth it. Okay. They did actually, even in System R in the 1970s, they considered both I/O and CPU costs at some course grade level. Obviously, things have improved a lot since then, and we'll learn a bit about what's improved in selectivity estimation. So the search algorithm we're going to use is a dynamic programming algorithm. All right, but first let's look at the plan space. So we're going to break the query into query blocks. I talked about this before. If you have a nested query, like this one up in the upper right, we're going to optimize it one query block at a time. So one select clause at a time, inside to out. So first we'll optimize the inner select block, and when that's done and compiled into a query plan, it's input to the outer optimization. Okay? So it's only one block at a time. If your nested block is uncorrelated, remember that has no references to the outer query blocks, then you can compute it once and store its result and cache the result. So we'll do that. All right, we'll be smart about that. If it's correlated, it's basically like a function call. So if you have an outer query block, let me draw a picture. All right, select from where, so let's say from T, comma, dot, 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 where, blah, select from where, let's say, T2, blah, 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 where, T1 dot something equals T2 dot something, right? So there's this correlation variable to the outer, where T dot something. Correlation variable, right? This thing is referencing the outer block. This is essentially like saying we're going to run this query, but we're going to pass in the value of T dot C as a function call. So it's like we're making a function call to this query where this is a variable v, and this query is like a function of v, and v comes from the current tuple of T. Make sense? So this whole query block is treated like a function call. The variable v, which fills in T dot C, comes from out here and is filled in one tuple at a time by scanning through the tuples of T. Okay, so that's how we're going to evaluate these correlated blocks. Sometimes, as I said, you could decorrelate and flatten, and we won't talk about this in this class. For each query block, now, this is kind of the core of the Selinger algorithm, the plans considered are all the available access methods for the leaves. So if you have a heap file and 3 indexes on A, we're going to consider that heap file and all 3 indexes on A as ways of accessing A. Same for B, C, and D. So all the ways of accessing the relations in the from clause. And then all left deep join trees, that is, trees that have this shape. A, join B, join C, join D. All right? The right branch of every join in a left deep tree is a base table. Those are the only plans we're going to look at. We're not going to look at these so-called bushy plans. I'll show you a slide on this in a minute. Within the space of left deep join trees, we're going to consider all the join orders, so all the ways of ordering up these relations, and all the join methods, so all the join algorithms that we know. So that's the plan space that Selinger considers. And I'll talk about the motivations for why left deep trees in a minute. Here's our schema, sailors and reserves. Blah, 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 blah. All right, yeah, let's do it this way. I thought maybe we would skip through this, but no. All right, so let's translate this SQL to relational algebra, as we talked about at the beginning. So here's a somewhat more complicated query. We're joining 3 tables, sailors, reserves, and boats. And the reason we're doing that is we want to look up properties of for each reservation. We want to look up properties of the sailor and properties of the boat. Okay? So we're going to join sailors to reserves on sailor ID. We're going to join reserves to boats on boat ID. The reason we want boats in there is because we're interested in red boats, and that's only stored in the boats table. So b.color equals red. And we're going to group it by sailor ID And we're going to have the minimum r dot day per group, but only for those groups where the count is greater than or equal to 2. Okay? So that's our little query. It's a 3-table join. First thing we can do is translate it to relational algebra, just for fun. This is a naive query optimizer. It said, okay, let's take the from clause. We'll join up everything in the from clause in the order you typed it. And then we'll select out the red stuff. And then we'll group by the SID. And then we'll do the halving. And then we'll do the aggregates. All right, so this is kind of the null query optimizer, the one that doesn't think at all. This is what we actually looked at early in the class when we were understanding what SQL meant. With that, we can think about what's legal in the relational algebra to translate this query to something better. All right, so this is the first thing we need to do, is talk about what are the equivalences in the relational algebra that allow us to consider other plans. So we talked about pushing selections down. So first of all, what can you do with selections themselves? If you have a selection with a conjunction of clauses, see where I am up here in the slide? That's the first bullet here, so maybe I'll use computer technology here we go. See this set of clauses? You can break that down into a cascade of selections. Those are equivalent. They mean the same thing, right? Conjunction and nested selection are the same thing. All right? And selections commute. So C1 of C2 is the same as C2 of C1. Make sense? Should make sense. All right, you can prove all these things, but it's boring. It's straightforward, right? Projections are a little weirder than that, actually. So the projection of A1 on R is the same as a cascade of projections where they're increasingly bigger on the interior. So look what happened here. We threw away AN, and then we threw away AN minus 1 and AN minus 2 until we were left with just A1. All right. So actually, you can always throw away more columns later, is the way to say that, way to think about that with projection cascade. Now, importantly for query optimization, Cartesian product is associative and commutative. So it's associative, which means R cross S cross T equals R cross S cross T, right? And let's draw that picture. Because we'll look at a lot of plan trees later. It's good to have a sort of visual sense of this. R cross S cross T, right? Which comes down here. The left-hand side of that equivalence is equivalent to R cross S, cross T. Right? The thing on the right is what we call the left deep tree. The thing on the left is actually a right deep tree. We're only going to look at left deep trees. These things are also commutative. So R cross S equals S cross R. All right? That's nice because they're commutative and associative. You can do them in any order. You can do cross products in any order, and it means the same thing. So, if you want to say R cross S cross T equals T cross S cross R with the usual binding rules, all right? That's nice. That's fine. You can reshape these trees to get from one to the other. Okay. Now you have to be a little careful. This is all also true for joins, because joins are just cross products with selections built into them. But you do have to be a little bit careful. So now, let's look at this example at the bottom of the slide. We have R cross a join. Let's say it's a natural join. S join T. What that means is that S and T share at least one column in common, and we have an equality match between S and T, right, on that column. Agreed? Natural join. Okay, so because cross products is commutative and associative, this seems like it should be equivalent to R cross S cross T. All right. Join. Good. And that feels pretty good, right? So here, we're still taking a cross product of R with something, right? And the result of that has the column that's shared with T, so we can take the natural join. So that's all good. I mean, it may not be a good idea, because now you're taking the cross product of something that might be big. Maybe T was making S smaller. right? But it's okay. But let's look at one like this, where we do R cross. Actually, even this one's not so bad. Yeah. I guess let's stop here. The thing that's weird is that S is now participating in a cross product instead of a join, right? The join was on ST pairs. There are no ST pairs available at this point, so we have to do the cross product. Let me give another example. Maybe this wasn't the best example. Here's a good example. R natural join S, natural join T. Good? Everybody agree? So just a perfectly reasonable query. There's overlapping columns between R and S. There's overlapping columns between S and T. Let's reorder this guy. Let's do R, T, and S. What's the operator between R and T? They don't have any columns in common, so it's got to be a cross product. And then R and S have columns in common, so we can do a join here. But this was a query that had no cross products in it. Suddenly, this query has an exponential blow-up because it has a cross product in it. Okay, this is what you want to be aware of. Really, what's happening is the selection that the join of R join S is essentially being applied as a selection here. Some selection on the R and S tuples that we're applying after we join up the ST pairs. Right? It's sort of happening too late for this pairing operation. So R is getting cross-producted with T. It's kind of a bummer. That can cost you enormously. So sometimes we might generate cross products when there's other plans that have no cross products. Okay. All right. More equivalences. You can push projection through selection. So you have something like droid. Select A equals 4 of T. All right? You can push the projection down below the selection, sort of, but we're going to need this A here to evaluate the selection. So the best you can do, you can't push the projection all the way down. You can't say, this is not equivalent. Project I of T, select A equals 4, because there's no A column left anymore. Right? So you're going to have to say I comma A, and then you get rid of the I. Get rid of the A, right? So you have to cascade this projection without skipping steps. We would say this is project of I. We would rewrite this as project of I over project of I comma A over select of A equals 4 over T, right? And then we would push that guy down there. So this is cascade of projections, and this is commutativity of projection and selection. Okay? Make sense? Similar kind of rules, in a way, apply to pushing selections below joins. We saw this before. If you have a selection here, maybe you won't see that because of the board. Let me write it over here. R, join S, join T. Let's say select... what's a good example? Select, let's start with something simple. R dot A equals 5. All right? You can take this operator here. You can certainly push it down there because the R dot A is available. Once you want to go below this join, you cannot push it down this way, right? You can only push it down this way because it's referencing R dot A. Right, so this is just straightforward variable scoping. You can only push selections down where the variable is in scope. Okay? And if you have a selection that's more complex, let's look at another example now. A more interesting example might be, take this join of R, S, and T, and I want a selection that's got R dot A or, R dot A equals 4, or S dot B equals 6. All right, well, we can push this through the top join. Right? We can push it down to here. But it's essentially a selection over the join of R and S because it references both R and S. So you cannot push it down either of these branches. right? Because if you pushed it down here and you threw away things where r dot a equals 4, you might miss out on some pairs r comma s where s dot b did equal 6. Right? So you can't tear this thing apart and push it down both sides. Okay. But generally speaking, there's often cases where you can push selections down. The other thing to remember is that selection of a cross product is a join. So our join S, our cross product S, selection, R dot A equals S dot B is equivalent to our join A equals B S. And that allows us to use our join algorithms and not form cross products. Okay. Now, we talked about how in SystemR there's a heuristic called left deep trees only. Where did this heuristic come from? It's just a heuristic, which means sometimes it's wrong. Okay, so I'm about to tell you something that doesn't always work. All right, but what's the intuition for left deep trees? Well, first of all, it allows us to restrict the space of plans. Just to be clear, the thing on the left is left deep. The other two things are not left deep. So the middle one is sort of deep in a way, in the sense that one side of each join is a base table, but it's not left deep. And the right-hand one is what's called bushy. All right? So neither of these are left deep. So the cool thing about left deep plans, and the intuition was, it was 1970-something, right? They hadn't even invented hash join yet. And the SystemR guys invented sort of merge joining. The Berkeley people are like, oh, that's a good idea. Didn't think of that one. Right? So people started with nested loops join and kind of grew from there. It's a long time ago. When you think about things with nested loops join and indexes mostly, like your MySQL, which is mostly the way their optimizer thinks, then these kinds of plans where the inner relations are either scans or indexes, these kind of plans are the pipelining plans. Think about it this way. Tuples of A stream through this, and you do lookups in B, lookups in C, lookups in D, and then they go to the output. So if you build iterators and left deep plans, this is kind of like basically plans on A. This is basically a big query on A with lookups into B, C, and D along the way, right? And so it's got this feeling of like streaming, right? It's got a small memory footprint because each tuple of A just kind of comes through and then disappears. You never materialize that outermost relation. And if you have indexes, they fit into the plan in a very natural way. And if you don't, it's just a nested loop. So this has kind of been the idea was that streaming behavior is to be encouraged because it lowers your footprint and it improves your throughput. This was totally blown up by MapReduce, which decided after every operator that you should put everything back down on the disk for fault tolerance purposes before you pick it up again. So there's no streaming in MapReduce, and so this intuition makes no sense in sort of a MapReduce system. But it made sense in a streaming system, which essentially the initial relational databases are, and which a lot of the MapReduce-style systems are moving back towards. All right? So it's a fairly natural thing to do, these lefty plans. It encourages you to think about pipelining and streaming and not materializing when you don't need to. Yeah? So we're going to do a lecture later on in the semester on big data systems like MapReduce and Spark. The motivation for it at Google makes perfect sense. Google runs a job on 100,000 computers. Odds are in the middle of that job, one of those computers will crash. As a result, every single step you take in one of those jobs, you want to make sure you can recover from crashes of the individual nodes. Okay, so what MapReduce does is that every worker that's doing a little piece of a join or a little piece of a sort writes down their output before anyone consumes it to a shared file system. So that whatever they did, that work is somewhere in a shared file system where some other worker could pick it up and proceed. All right, so it's worth writing things down to disk. It's actually worth replicating it across the network on disk, a shared file system, so that someone else can pick it up and take the work from there. The thing is, there's like 5 companies in the world that run jobs that big. And for everybody else, they got like their 10 machines, and they're doing all this writing stuff to disk in case one of them fails in the middle of the job. The job might take 5 minutes. The odds that one of 10 machines fails within those 5 minutes is super low. So you're doing all this I/O for fault tolerance that you didn't need. Right? Back in the 70s, there was one machine, one processor, and it definitely didn't fail mid-query except once in a blue moon. Right? So it's when you have 1 million machines running for you, yeah, you're going to have failures mid-job. And that was the motivation. And for Google, it made a ton of sense. And for the whole community that went crazy about Hadoop, it pretty much didn't make any sense. And it still doesn't make sense for more than a handful of customers, actually, or users. So Spark went a long way towards fixing that, actually, by keeping things in memory rather than writing them to disk all the time. But even Spark doesn't stream. So this is all being revisited. But people got kind of Google mania in the 2000s. Like, we'll do everything the way Google does because we also run the world's largest internet data service. No, I mean, that wasn't the reasoning. The reasoning was supposed to be they're supposed to be smart, right? But they had a different problem than most people have. They were optimizing for different things than most people should optimize for. So since you dragged me down that rat hole, I will say that just because it's being done at scale doesn't mean it's being done intelligently for other scale points. All right, let that be a lesson to you. Just because Google does big things doesn't mean they do smart things all the time. Sometimes they do smart things for big things, but they'd be dumb things for small things. And small can be pretty important, like almost every job on the planet. Okay, rant over. All right, so that's why I left deep trees. And you know what? They work out pretty good. The other thing you can study, which people have studied over the years, is, okay, what are we giving away with these other tree shapes, and when do they dominate? And the answer is, yeah, sometimes they win, and we could try to characterize when, but it's not like they win so much that this was a fatal flaw. Left deep trees usually do pretty good. All right. Let's talk about cost estimation. So this is actually an incredibly deep subject, totally unrelated to the rest of the stuff. So we don't have to think about plan spaces. All we have to think about is individual operators, input sizes, and output sizes, and input data and output data. We don't have to think about the plan space. We don't have to think about the search algorithm. It's very isolated and clean, and it's hard. This is a hard estimation problem, all right? And you can kind of, like talking about rat holes, you can definitely go down the rat hole on this one. So you can also be really silly, and you want to be somewhere in between. So it's a fine line. All right, for each plan we consider, we have to estimate the total cost of that query plan. What is the cost of the query plan? It's the sum of the costs of all the nodes in the query plan. That's all. Okay? So we have to estimate the cost of each node or each operation in the query plan. What is the cost of something like a sort merge join? Well, you guys know. It's a function of the sizes of its inputs. Right? You need to know how many tuples, how many blocks at the input, and that'll tell you how much it's going to cost to do the sort merge join. So we've discussed this in class, right? But if you need to know the costs of your inputs in any closed language where you can pipe things into other things, then you need to know the sizes of the outputs like this, right? Because actually I just erased what I should have saved. If we're doing our sort merge join S, chunk nested loops join T, you can tell me based on what we've learned in class how much this will cost if I will only tell you things about R and S. That's fine. But if I tell you things about R, S, and T, and I ask you how much this will cost, your job, which I haven't taught you how to do yet, is to estimate how big this thing is, the input to that join, which is to say you have to estimate the size of the output of this join. And that's the tricky bit. Okay? So you have to estimate the size of the results for each operator in the tree other than the root, because that determines the downstream, meaning up the board, input cardinality. Downstream in the data flow, right? The data is flowing this way, so if there's a stream, it's going up the board. And the way we're going to estimate this has got to be based on the information we have, which is information about this and this and this operator. So I want to know some things about R and some things about S and some universal truths about join, okay, to be able to figure out the size of the output R join S. All right? So we're going to make some strong assumptions along the way. One of them is we're going to assume independence of predicates. We're going to assume that in a big, long query plan, each one of the subscripts, so, R.A equals S.B, S.C equals T.D, we're going to assume that these predicates are independent of each other, which in general is going to be false. Okay? Simple example. This is sailor ID. This is reservation. This is reservation again. And this is boat color. Maybe highly rated sailors like red boats. All right? In which case, there's a dependence between what sailors are associated with reservations and what boats are associated with reservations. All right? And in general, you would want to have that high-dimensional correlation matrix to figure out the exact numbers here. We're not going to do that. We're just going to assume that if you know this is 1/10 and you know this is 1/10, then the query is going to put them together and get you 1/100th of the output. All right? And we'll go through this calculation before, but I just want you to realize we're making strong independence assumptions up front. Okay. Now in System R, which is actually not that far off what people do today, the cost is going to be boiled down to a single number for each query, for each plan. And that number is going to be the number of IOs it does. In System R, they didn't even consider whether they were sequential or random. In Postgres, they at least separate sequential and random, okay? But the number of IOs is all we'll talk about in this class, plus some fudge factor times the number of tuples. All right, so if you have a number of tuples that come out of a query, assume every tuple needs to have a massage, and that massage has a constant cost, all right? CPU massage cost. And we won't worry about the details of whether hash join uses more CPU cost than sort merge join. All right, we just assume there's this constant kind of massage a tuple cost, all right, which is a fraction of an IO. All right. Given all that, the question on the bottom of the slide should be easy. Is this cost estimation the same as runtime? Is it a good approximation of runtime? Probably not, right? If we're saying, well, sorting costs the same as hashing costs the same as looping in memory, actually we didn't even measure the cost in memory. Maybe we do an exponential algorithm in memory. We're not taking very careful accounting of that. So costs here are pretty sloppy. This metric also doesn't separate sequential and random IOs. And then don't forget that we're making these crazy assumptions, like independence assumptions, that are going to make our inputs to these cost formulas wrong, too. So people have, over the years, tried to use query optimizers to estimate the true runtime of plans, and it always works terribly. But the relative ranking of these query plans, is this plan better or this plan better, is somewhat less sensitive. Usually, even though the estimates are wrong, it's like this one's super expensive and this one's not expensive. That kind of remains true, even with all the errors we're making in this estimation process. So remember, the optimizer's goal is to kind of rank order these plans, not actually cost them out. We want to find one that's at the top of the rankings. It's cheapish. All right. So how are we going to do that? Well, first we're going to start with some information about the base tables, statistics in the database catalog. All right. So we're going to want to know what relations we have and what indexes we have. And the catalogs will typically contain, at bare minimum, the following statistics. So this is the System R 1970s era statistics. How many tuples are there in each table? Let's keep track of that. How many disk pages are there in each table? Let's keep track of that. Those are the two statistics we've been using so far to estimate the costs of our algorithms, right? Okay, but we'll also keep, for every column, the minimum value and the maximum value. And for every column, we'll keep the number of distinct values in that column. All right? If I know the minimum, and I know the maximum, and I know the number of distinct values, think about it, drawing a picture. Let's say I'm looking at Saylor ratings, and I know they go from 0 to 10, and I know that there's exactly 10 possible values in here. Or even better, let's say there's only 4. There's only 4 distinct ratings in my data set right now. So that's pretty good. I can estimate that, 25% of my tuples are one of 4 things, right? It's sort of like a weird kind of plot of how we distribute our data that's like a big square. We sort of uniformly spread it across 4 values. We actually don't know where those 4 values are here, but we know there's only 4, all right? So we can kind of discretize this thing into 4 chunks, say all the chunks are about the same size. It's kind of like a bar chart or a histogram, but it's a really dumb one. Because all the bars are the equal height and all the bars are equal width. Okay? For an index, because we're going to have to pay the cost of walking down it, let's keep track of how tall it is. And we'll also keep track of how many pages is in that index. All right, so those are base statistics, very simple ones. Now we're going to update these only periodically. You don't want to update these on every insert, because that means every insert is 2 inserts. It's an insert into the table and an update to the statistics. So that's just expensive. We'll do it off in the background. And look, there's a lot of approximation going on in this whole business, so it's okay if we're a little out of date. All right, so maybe this runs in the background in a background thread. Maybe it runs once a day, whatever. This is really baby stuff. So modern database systems, particularly the commercial guys, have invested a lot of money. So Microsoft and IBM and Oracle, the sort of very old, mature databases, have a lot more statistics baked into the optimizer. We'll talk about some of them. Among other things, they'll keep better histograms than this. Okay, that's sort of where it starts. And it kind of goes from there. And we'll talk a little bit about that. All right, let's do some simple size estimation using those basic statistics. All right. So the maximum output cardinality of any query block, select from where, is the product of the input cardinalities. Because the biggest thing you can do in the relational algebra is a cross product. Right? That's the growingest operator we got. So we know that things are no bigger than the product of the input cardinalities. The question is, how much smaller is it than that? right? And this goes back to our trivial query plan, the one we started the class with, which is the one where we have all the cross products with a big selection on the top, right? So if you have a big query on 4 tables, R, S, T, and U, think about it as R cross S, cross T, cross U, with a giant selection on the top for everything else in the where clause. You know at this point how big the output is, because the cross product is the product of the cardinalities of the tables. The question is only how much are we throwing away with this big selection at the top. So the selectivity is what we want to estimate. How much are we throwing away? And each term in the where clause, each one of these outer conjuncts in the where clause, you see the where clause is term 1 and blah and term k. Those outermost conjuncts of the where clause, we'll call those terms. Okay? Each one of those terms has a selectivity that we want to estimate. And what we're going to do is assume the terms are independent and multiply their selectivities together to get the selectivity for the whole query. So the selectivity associated with each term reflects the impact of the term in reducing result size. It's the size of the output of that term over the size of the input of that term. So when we talk about selectivity, it's always size of output over size of input. How much smaller did things get? Notice that size of output is always smaller here, so this is always a number less than 1. It's a probability, actually, is what it is. It's the probability that a tuple will make it through that term. Okay? So it's a number between 0 and 1. Selectivity, so the result cardinality is going to be the maximum number of tuples, which is the cross product of all the tables, times the product of these selectivities of the terms, because we're assuming they're independent. So we can multiply, if this term throws away 9/10 of the tuples, and this term throws away 9/10, then they each have selectivity 1/10. 1/10 times 1/10 is 1/100. All right? So that's an independence assumption, though, between my two hands. All right? So just note that the book calls selectivity reduction factor, but everybody else in the universe that I know calls it selectivity. Every database person calls it selectivity. Here's a sort of confusing thing. Highly selective in common English is the opposite of what it means here. So when we say Berkeley's a highly selective college, what we mean is that it admits very few people. But high selectivity here, like 9 out of 10 tuples go through the output, is the opposite. That's like, I don't want to say what school, but the schools that let 9/10 of their students in, right? So when we say a predicate has high selectivity, that means it lets through most of the tuples, size of output over size of input. Okay. Cool. So here's where things get weird. We'll do this today, and then we'll maybe finish it tomorrow or review it. Not tomorrow, but next time. Let's do our result size estimation for different kinds of terms. Most of these are straightforward, and then there's some that are kind of head-scratchers. So the result cardinality, remember, is maximum number of tuples times the product of the reduction factors. So what is the reduction factor for a term that's of the form column equals value? Sailor ID equals 100. Okay? Well, given that we know the number of distinct keys on that column, we know there's 100 different sailors, then we could say that the reduction factor is 1 over that, right? Equality selection, column equals value, is 1 over the number of distinct values. And that's a uniformity assumption on the domain, right? We say, well, if there's k distinct values, then it's equally likely that each one of those k is going to come out. That may be a terrible assumption, but it's the assumption that we're going to make for now. All right? We'll make it better next week. All right, but that's the sort of basic system R assumption. All right. What about column 1 equals column 2? All right, that comes up in joins, obviously. It also comes up in single tables. You could say, I want to find all people whose first name is the same as their last name. More typical that you see it in joins, though. All right, but remember that saying that sailor ID in sailors equals sailor ID in reserves, which is the usual join case, right? So we have sailors, and we have reserves, and we say sailor ID equals sailor ID. This is the same as S cross R select SID equals SID2 or whatever, right? So really, this is just a selection on a single table. Oh, that table got generated by a cross product, but whatever. So there's really no conceptual difference between last name equals first name and reserves.sailor ID equals sailors.sailor ID. All right, so here's the expression for it. It's 1 over the larger of the two cardinalities. It's a little weird. 1 over the bigger one, which means that we're getting a smaller number, right? Because the denominator is the bigger of the two choices. Why would the selectivity be the smaller of the two choices? Yeah. One intuition comes from joins, but another intuition comes from bunnies. So let's do bunnies. You can't really tell that their ears are different colors on this screen, but they are. All right, so what's the probability? If we have bunnies and they could have different colored ears, what's the probability of a bunny with 2 ears of the same color? All right, let's say we have 100 bunnies, and there's 2 possible colors for the left ear, C1 and C2. There's 10 possible colors for the right ear, because this is what happens with bunnies. I don't know. It's genetics of bunnies. You learned it here. All right? And the ears are independent trials, okay? So what's the probability that the left equals the right? Well, it's the sum over all colors of the probability of getting that pair of colors, right? It's the sum of red, blue, green, green, etc. All right? But keep in mind, there are only 2 distinct left ear colors, and there's 10 distinct right ear colors. And the only matches, so P of C1, C1 plus P of C2, C2 plus P of C3, C3, but the only matches are 1 and 1. And 2 and 2, right? So the first clause here, P of C1, C1, is a half of the left ears times a tenth of the right ears, right? Probability. Second one, 50% probability that the left ear is C2. 10th probability that it's C2 on the right ear. And the rest of them, those colors don't appear on the left ear, so they're 0. Add this all up, it's 1/10, not 1/2. Does that make sense? Right? When you add this up, because the options that are not available on the left-hand side kind of cancel out on the right-hand side, you end up with just the 1 over the max. Right? And you could try this a couple times and kind of convince yourself of this, but it is 1 over the max, right? With all the independence assumptions that we made. Okay, so that's the weird one. Column 1 equals column 2. It's just, I never found it intuitive, but it is true with all those independence assumptions being made. Now, if you have column greater than value, you need to think about kind of somewhat bigger ranges. So you want the maximum value minus the value in the query. It's worth drawing a picture, right? And I erased the one we had. So we have a distribution of ratings of sailors, let's say, between 1 and 10. And I want rating greater than 5. And we're making a crazy uniformity assumption on ratings of sailors. So this is the x-axis of ratings. This is 0. This is 10. This is ratings. I want to know how much stuff is there from 5 up to 10, right? So it is the number of values, with the maximum value being 10, minus the value in the query. So this is value. And this is high of I. The maximum value stored, okay, over this should be 1. This minus that over the full range. It's the range of the query over the range of the data is the selectivity, right? And there's a +1 in there to make it work right, because, right, that's the old trick. How many fingers do I have? I have 11 fingers, right? 10, 9, 8, 7, 6, and 5 is 11. Did your dad ever do that to you? You have to be careful with your off by ones. All right. So that's term column greater than value. Huge independence assumptions and uniformity assumptions baked into all of this, all right, which are often wrong. Oh, by the way, the Selinger paper has this great piece of advice, which is if you don't have the relevant statistics in the catalog, then the selectivity is a 10th. Because it is. Because you need to pick something. So their magic number is a 10th. If you don't know any better, say it's a 10th. Fair enough. Okay, so we looked at the probability of left ear equals right ear. Let's look at what Postgres does. This is the latest version. I went and refreshed this slide, which means to say it's the same as it was 3 years ago. And I double-checked. All right, so here's the default selectivities in Postgres for things. The default equality selectivity, if they don't have statistics on the tables, is 1/200th, it looks like. Not a 10th. So things have progressed since 1970. We've gone from a 10th to a 200th. The default inequality is a 1/3 for some reason. I mean, so these are just in there for when the optimizer doesn't know any better. You have to put something because it's software and it needs a number. Right, but my favorite default selectivity is this one, which I put in 1992, and they haven't taken out. Yes?
Are the tables that store the stats? There are, I don't know if that's how they work. Are those like just recursive?
So the tables that store the stats are in the catalog, and they're exactly that information that we had here. They're not. So what's better today, which will be maybe a subject of next lecture, but we do many more things than this today. But they're all refinements to this, in essence.
Are they stored like as SQL tables?
Yeah. Oh, yeah. I mean, we could fire up Postgres, and there's a tables table, and it has information about the tables, which includes the number of tuples and the number of blocks. And yeah, I encourage you to poke around in the system catalog. Maybe it's later in the slides. So yeah, this one was put in 1992, and I put it there, and it never changed. And we're now on v9.4, so that's bad. Okay. So what we'll pick up next time is we'll do better than uniformity assumptions. We'll start looking at histograms and capturing the distributions of these columns to get somewhat better probabilities for the outputs. Okay? Your homework, before you go, is being passed out today. It is due a week from Friday. So this is a dense amount of time. There's plenty of time to do this homework, but you cannot shilly-shally or dilly-dally. You'll have to get started pretty much right away. Okay? So the homework is still due next Friday before spring break. It is eminently doable in that amount of time. It will be that awesome function caching, joining, rest call awesomeness that we described last time. That should be out today. See you soon.